Hello and welcome to our video for section 9.8 on power series. This is what we're going to be doing here is going to be taking our next step. In the last section, we dealt with Taylor polynomials and Maclaurin polynomials. Now we're going to move this into power series. And so no longer is it going to be a finite degree. Basically, a power series, you can think of it as an infinite degree polynomial, if you want. So our objectives for this particular video are: number one, understand the definition of a power series. Number two, find the radius and interval of convergence of a power series. Number three, determine the endpoint convergence of a power series. And number four, differentiate and integrate power series. These are going to be functions of x. Okay, the power series are going to be functions of x. So as functions of x, we are going to integrate them and take the derivative. But please keep in mind, we are dealing with polynomials. Okay, and so really when we deal with the derivatives and integration of these, we're really just going to be using the power rule, which I think you'll recognize when we start working on those. So let's look at a definition of a power series. If x is a variable, then the infinite series of the form n equals 0 to infinity of a sub n x to the n, which is a sub n, or a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed, and so forth, all the way down, is called a power series. More generally, n equals, the sum as n goes from 0 to infinity of a sub n times x minus c to the n, of a0 plus a1 times x minus c to the first plus a2 times x minus c squared plus a3 times x minus c cubed, and so forth, is a power series centered at x equals c, where c is a constant. Now, the first thing I would hope that you're recognizing on this one is you're saying, wait a second, these particular series look very similar to the polynomials we were working with last time. That, in essence, the difference between what we were working with and what we are dealing with now is that these go on where the other ones had a finite degree. And that would be a very accurate description on this. Okay, this is what we're looking at with the power series, is really just doing an extension of what we were working on before. So a couple examples. Let's just take a look. These are all power series. And so when I look at each one of these, what we really want to do is identify where is this one centered. So in this case, in this first one, we know when you look at it, you have x to the n. So in this case, this is c, the c equals 0. So x minus c, so c is 0. In this next one, I have x minus, it's negative 1 to the n times x minus 2 to the n. So in this case, c would be equal to 2. And in the third one here, I have 2 to the n, x plus 3 to the n over n factorial. In that case, c is equal to negative 3. So those would be the center values of those. So once we go through and work with this, we want to go through these power series. The interesting thing about them is power series will converge. They can converge or they can diverge as well. Okay? And where they're going to converge is they're going to converge for values of x. Some values of x could converge, some values of x could diverge. Okay? The upshot is this. Every power series, every single power series does converge at some point. There is no power series that is going to completely diverge. Every power series is going to converge. It's just a matter of what type of convergence, where it could converge at. Okay, so the first thing is, when we talk about it, it could converge only at the center point. Remember, c, when you look at a power series, that very first term is equal to f of c. Okay, so it will, at the very minimum, it will converge at its center point. So in some situations, our power series is only going to converge at x equals c. It will diverge every place else. Other times, the power series is going to converge for all x. Okay, and no matter what x value you plug in, you're always going to get a convergent series. Okay. The third thing is that there's going to be some number r, where it's some positive number r, such that if x falls within r units of c, if the absolute value of x minus c is less than r, then the series is going to converge absolutely. But if the absolute value of x minus c is greater than r, the series is going to diverge. Okay. Now that value of r is called the radius of convergence. Okay. Now the thing that happens with that, one of the things we're going to be asked to do is we're going to be asked to find an interval of convergence too. So some things to keep in mind on this. Like we said here, the value of r in number 3 is the radius of convergence. In the first two, we do have a radius of convergence there as well. In this first one, when we converge only at c, we can say that the radius of convergence is equal to 0. And when we are going to converge for all x, we could say that the radius of convergence is going to infinity. We have an infinite radius of convergence. Okay. If the radius of convergence is finite, then we're going to be dealing with an interval of convergence that we have where there's going to be some real number endpoints that we have to deal with. Okay. So now, once we know what that radius of convergence is, our next job is going to be to find the interval of convergence. So what happens to find the interval of convergence? The first thing I have to do is find the radius of convergence. And I'm going to find the radius by convergence by really setting up the ratio test. And then I'm going to take, remember the ratio test was the limit as n approaches infinity of a sub n plus 1 over a sub n. And we would go through and we knew it would converge if it was less than 1, it diverged if it was greater than 1. And if it was equal to 1, we couldn't say anything. So what we're going to do though, is we're going to go through this. Remember, this is a function of x. So we're going to set this up, our power series, do the ratio test with our power series. So we'll even have it. So I'm going to have the a sub n plus 1 times x minus c to the n plus 1 over a sub n times x minus c to the n. And I'm going to take that absolute value, the limit as n goes to infinity, I'm going to say it's less than 1. I'm already going to start out with less than 1 because I know that's going to converge when this is true. And so what I'm going to do is I'm going to go through with the ratio test. I'm going to simplify that expression. I'll do like I did with the ratio test before. I'll rewrite it in terms of a multiplied by the reciprocal. I'll simplify the expression. But the end result is I'm going to want to end up with something in the form of x minus c is less than r once I take that limit. Okay? Once I do that, now I'll know what my radius of convergence is, and I know then that x minus c, the value of x minus c, is going to fall between negative r and r. So I'm going to rewrite it as a compound inequality, and I can solve for x. So I get negative r plus c is less than x, less than r plus c. And that now gives me an interval of values, and I have these endpoints. Once I know what those endpoints are, I do always have to check the endpoints to determine if we are convergent at each endpoint or not, okay? In some cases, some situations, I will converge at an endpoint. In other problems, I will not converge. So whenever you're finding an interval of convergence, once you know what the endpoints are, you must always test the endpoints. Take a second, pause the video, make sure you're comfortable with this, write down any questions that you have, and then we'll move on. So right here, I have two different examples, one in yellow, one in green. Okay, let's start out with the one in yellow. So our power series in this case is the sum as n goes from 0 to infinity of n factorial times x minus 1 to the n. So I set that up with the ratio test. So it's going to be the limit as n approaches infinity of the absolute value of n plus 1 factorial times x minus 1 to the n plus 1 over n factorial times x minus 1 to the n, and I'm going to say it's less than 1. And now what I'm going to do is reduce this. So in this particular problem, n factorial will go into n plus 1 factorial, and so it just will be left with n plus 1, and x to the n minus 1 to the n, x minus 1 to the n goes into x minus 1 to the n plus 1, and it gets rid of that, so it's going to be to the first. So the end result is, when I reduce this fraction here, I'm going to get the limit as n goes to infinity of the absolute value of n plus 1 times x minus 1. And I'm going to say, again, that that is less than 1. Keep that less than 1 there. Well, here's the thing now. No matter what x value I pick, as n goes to infinity, n plus 1 is also going towards infinity. And so this limit here is going to be infinity times x minus 1. And to say that's less than 1, that is false, because no matter what x is, when we go up, we're never going to go through. It doesn't matter how close x is to 1. If I multiply it by bigger and bigger and bigger numbers, I am going to go off to infinity. So this thing right here is not less than 1. This is a false statement. This will never be less than 1. So therefore, my radius of convergence in this case is 0. And this particular power series will only converge at our center point at x equals 1. Okay? So when we took the limit, when that limit here goes off towards infinity, that's telling you that radius of convergence is going to end up being 0. Now let's look at the one in green. In this case, we're taking the limit as n goes from 0 to infinity of x to the n over n factorial. So I write that out. It's going to be x to the n plus 1 over n plus 1 factorial. That whole thing over x to the n over n factorial. And I'm going to set that less than 1. When I simplify that, I'll rewrite that as a multiplied by the reciprocal. And now I'm going to simplify it. And again, what's going to happen here, x to the n is going to cancel out almost everything but 1 of the x to the n plus 1. So it's just going to be x to the first there. And n factorial is going to go into n plus 1 factorial. And the end result is that this is going to end up being, this expression here will end up being x over n plus 1, or I can write it as the limit as n goes to infinity of the absolute value of 1 over n plus 1 times x. And I say that's less than 1. Now, I generally will write it in this way. I'll pull that x's out and I'll just have all anything dealing with the n's separate. But I take the limit now as n goes to infinity. So as n goes to infinity, this is going to be 1 over infinity, which we know is 0. So the result here is that this limit is going to be 0 times x. Well, 0 times any real number is going to be 0, which is guaranteed to be less than 1. So therefore, this is always true. Where this one over here was always false, this one over here is always true. So for this particular problem, our radius of convergence is infinity, and we're going to converge absolutely on the interval from negative infinity to infinity, or for all real numbers. So our interval of convergence here is negative infinity to infinity. Okay. Pause the video here. Identify any questions. Make sure you're comfortable with everything. Identify any questions that you have. And once you're comfortable or you have all your questions, move on to our next example, which is really going to get us into one that's where our radius of convergence is not 0 or infinity. Okay, so for this particular problem, we're going to take the series as n goes from 1 to infinity of x to the n over n, that power series. So I'm going to take the limit as n goes to infinity. I'm going to set this up. It's going to be x to the n plus 1 over n plus 1 all over x to the n over n, and that's less than 1. Now remembering what I'm going to do on this one, I'm going to take this and multiply by the reciprocal. So this is now the limit as n goes to infinity of x to the n plus 1 over n plus 1 times n over x to the n. Now I reduce that at this point, and the x to the n is going to cancel out everything but one exponent in that numerator on that first one. And notice we can't really eliminate anything with the between these two. So the end result is that this whole expression is going to become the limit as n approaches infinity of the absolute value of n over n plus 1 times x, and that's less than 1. As n goes to infinity, this is going to be infinity over infinity. Again, you either recognize it with horizontal asymptote or L'Hopital's rule. The end result is this limit here, as n goes to infinity, is going to be 1. So what we get on this particular problem is that the absolute value of x has to be less than 1. Now remember on this, the center point for this one is 0. So we are at this point where it's x minus c, so x minus 0. And so our radius of convergence in this case is 1. So that now tells me that the values that this is going to converge when the values of x are between -1 and 1. Okay, so that's a start. Now the next thing we have to do with this, we have to check the endpoints. And so what I'm going to do on there, when I check the endpoints, the first thing what I'm going to do is I'm going to plug those endpoints into this particular power series. So when I put x equal to -1, if x equals -1, then my power series is going to become -1 to the n over n. And that particular power series, you might recognize that is the alternating harmonic series. And so we know it converges. That particular series converges. So we will converge at x equals -1. So I'm going to want to make sure that when I do my final interval of convergence, that I include -1. The next one, if I let x equal 1, that's our other endpoint. Then I'm going to put 1 into here. And so what I'm going to get at that point, I'm going to get the series 1 to the n over n, which equals the series 1 over n, which that's the harmonic series, which we know diverges. So therefore, our interval of convergence on this one is the interval that's bracket -1 to 1 with a parenthesis there, because we are including -1 but not +1. So that would be our final answer for the interval of convergence. Okay, remember, once you're at this point here where we get the radius of convergence, we want to write it out here, get that series solved, get it as x in the middle by itself, and then we always will need to check those endpoints. Again, as before, pause the video, make sure you're comfortable with these calculations, and once you are, we'll move on to the next part. All right, so one of the things you have to keep in mind, f of x is a function, okay? F of x is a function, and we're going to say f of x is equal. It's a function that is also equal to this power series. It has a radius of convergence of r greater than 0. If it does have that, then there's an interval of convergence, okay? And on that interval of convergence, f is differentiable and therefore continuous. Remember, if a function's differentiable, then it's continuous. So on that interval of convergence, it is going to be differentiable. and therefore continuous. And because of that, we can find the derivative and integral of our power series. Okay? Now, it seems a little scary. I know when I first heard this, I was a little nervous about it too. But remember, all you're doing is the power rule. This is, in essence, this is a polynomial. And so when I go through and take the derivative, I'm using the power rule. So I take the derivative of this. It's going to be the sum as n goes from 1 to infinity of n times a sub n times x minus c to the n minus 1 power. Okay? Next. Oh, in this case, why, it was 0 there. We changed it to 1. The reason is because if n was 0, that would be 0 anyway. So it would go away. Okay? So that's why we have the 1 there. Then we integrate this. The integral, again, doing the antiderivative of the power rule, it's going to be the integral of f of x dx is going to be c plus the series, n goes from 0 to infinity, of a sub n, the antiderivative of x minus c to the n is x minus c to the n plus 1 over n plus 1. That will be the antiderivative. Okay. Now, the other thing that you have with this, one thing that's kind of unique about this. Now, remember, so we can go through, we can have a power series for a function. We can take its derivative. We can take its integral. That power series has an interval of convergence that we started with. When we take its derivative and its integral, the radius of convergence and the center point are going to remain the same. So because of that, I know that all of these will have the same interval of convergence, except possibly at the endpoints. Okay, so when I go through, if I have a power series and I know that its interval of convergence is all real numbers, when I take its derivative or its antiderivative, its interval of convergence will also be all real numbers. Okay, if I have a power series that has an interval of convergence from 1 to 5, say, then its antiderivative and derivative are going to have that same 1 to 5 interval of convergence. The only thing that will happen, though, is I will need to check what happens at the endpoints. That will be the only place where there could be a difference between the interval of convergence of the original and its derivative and antiderivative. So let's take a look at what we mean. We just went through, earlier we went through and we found the interval of convergence for this particular series. N equals 1 to infinity of x to the n over n. And we know it converges from -1 to 1. The radius of convergence was 1. Center is 0. But we're including -1 and we're not including 1. Okay? So when I take the derivative of that, so I took the derivative here, I took the n down in front, so I get 1 over n times x to the n minus 1. That's going to simplify to x to the n minus 1. But what I know on this, I know that I'm going to converge, for sure when x is between -1 and 1. I already know that because that's what our original series converged for. It definitely converged from -1 to 1. We just had to check the endpoints. But notice what happens here. If I let x equal, if x equals -1, I have the series -1 to the n minus 1. That's going to diverge. okay? And if x equals positive 1, I'll get the series from 1 to the n minus 1, and that is also going to diverge. So in this case, my interval of convergence on the derivative is going to be the open interval from -1 to 1. It's going to diverge at each endpoint, okay? Whereas if I take the antiderivative, so I took the integral of this particular series, I know it's going to come out using the power rule, x to the n plus 1 over n plus 1 times n. I have that. Okay? And so, again, I know that it's going to, for sure, our center point is 0, our radius of convergence is going to come out to be 1. So I know -1 less than x less than 1. I now have to check the endpoint. Well, if I plug in the endpoints, okay, so if x equals -1, the series I'm going to get is -1 to the n plus 1 over n times n plus 1, which that is an alternating series. That's going to converge by the alternating series test. By that alternating series test. If x equals +1, then I get the series of 1. Basically, it's 1 to the n plus 1, which is 1, over n times n plus 1, which that will converge by the limit comparison test to the convergent p series 1 over n squared. So this converges as well. So therefore, our interval of convergence here is the closed interval from -1 to 1. Okay. Again, take a minute here. Make sure you're comfortable with each one of these calculations that I did. And if you have any questions, make sure you write those down and make sure to ask them in class. Okay. This does conclude this particular video on power series. So with that, I hope everything is going well. And again, if you have questions, make sure to ask them, and I look forward to seeing you in class.